Hello there guys, and then welcome to this video on limits. In this video we'll be looking at the limits of trigonometric functions. The limit of trigonometric functions. In our previous videos we've looked at the limit of polynomial functions and then the limit of rational function. Now in this one we are looking at the limit of trigonometric functions. If this is your first time on this channel, this is how beyond numbers will make maths easy to learn. If you find this video helpful at the end of the video, kindly choose to subscribe and then stay updated on any content relating to mathematics. Now on the other hand, you can always let me know at the comment section if you have any peculiar question or topic you'd want me to make a video on for you. Without much ado, let's quickly go into today's topic. We are on limits. Now there are some trigonometric functions that you wouldn't even need to solve their limits. They are constants and you'd always have to know. They are what? Constants and you'd always have to know. The very first of such kind is the limit of sine of a value. So the limit of sine x. What we see here is the graph of sine. So this is between -6 and 6. So if you want the limit of the sine at any value of x, it is just you evaluating the sine of that value. So the limit of sine x at any value of x simply means evaluate the limit or evaluate the sine at that particular value. So with what we have here, it simply means the limit at x equals 0 is 0. You see? So you just put in the values. The limit at x equals 6 will simply mean you also put it in there and then look for its corresponding value in that order. So the limit, so in conclusion, the limit of sine x is simply sine x. Let's take another one. Now this one here is the limit of the cos or the cosine of any value. So the limit of the cosine of any value is simply what? The cosine of that value. These two we are looking at, the sine and then the cosine, is just like how we did the polynomials. You just substitute the values of the a and then that will be it. So the limit as x approaches 0 would be what? 1. You get it? In that order. So these ones are just constants that we would have to know. Now let's look at the limit of other trigonometric functions. The limit of other trigonometric functions. And for this here, let's look at the limit of sine x over x. The limit of sine x over x. This here is the graph of sine x over x. So the limit of sine x over x as x approaches 0. As x approaches 0. So this is our graph we have over here. You see? And then as x approaches 0, both from the right and then the left hand side, we are getting what? A value of 1. A value of 1. So this is also one of the constants you will need to know. The next one here is what? The limit of 1 cos x all over x. The limit of 1 minus cos x all over x. As x approaches 0. So this is its graph. This is the graph of 1 minus cos x all over x. So as x approaches 0, as you can see, its corresponding value of 0. So as x approaches 0, both from the right and then the left hand side, we get a value of 0. That is fine. Okay, so for this, let's look at the limit of tan x over x as x approaches 0. Now, this is the graph of the function. You see, the graph of the function. And let me zoom in so you see why we are saying the limit of it equals 1. The limit of this function here is equal to 1. So I'm trying to zoom in. As you can see what we have over here, as you can see, this line here isn't directly on 0. It is not on 0. You can see there are spaces over there. You see? And then looking at the scale, if you look at our scale that we have here, then you see it is exactly not on the 0. It is actually on the 1. That is why we are saying, as we have plotted this graph, the limit as x approaches 0 should give us what? 1. Now that we have looked at the limit of some of the basic trigonometric functions, let's try and apply it to solve other complex ones. So this first one says we want the limit of sine 5x all over 5. This one here says we want the limit of sine 5x all over x as x approaches 0. Now, the limit we looked at, the one that is easily related to this one, is what we considered, which says the limit of sine x over x as x approaches 0 is equal to 1. I hope you remember this one. Let me quickly go to that so that you'd appreciate that. So this was it over here. It says the limit of sine x over x as x approaches 0 is 1. Take note that what we have as the denominator is the same thing you have as the input for sine x. Do you see? So now let's come back to our question and see how we relate this to get the answer of that. So our question is, we want the limit of sine 5x over x as x approaches 0. This we have here as the denominator is not the same as what we have as the numerator. So we need to transform it to look as that. And how do we do that? You should know that if we have to multiply this whole thing by 5 and divide it again by 5, it will still yield to 1, the same answer. So applying that concept in algebra, we are going to rewrite this whole thing as the limit of 5 times sine 5x over 5x as x approaches 0. And just note that this 5 here cancels this 5 here and still gives us this one. But if it is as this, we can't just solve it. You see, we can't just solve it algebraically. We can't just solve it. So we want it to make it look as this over here. That is why we are introducing this constant here. So now that we have that, it appears this alone looks like this function we have over here. Hence, we can bring out this 5 out because it's a limit of a constant. So that we are going to get 5 multiplying the limit of sine 5x over what? Your 5x as x approaches 0. Now this then can be compared to this. You see, because what we have over here here looks the same as this. And our general formula says if what you have as the input of sine is the same as what you have as the denominator, then it's equal to 1. So this simply means that we are going to get, remember we have our 5 over here. So we are going to get a 5, then times the limit of all of this gives us 1. So times 1. And evaluating it, we get what? A 5. So this simply implies that the limit we're solving for, the limit of sine 5x all over x as x approaches 0 is what? Equal to 5. Very simple. right? If there is anything I've done here, because we have applied some algebra and then other concepts that are beyond the scope of limits here. If you want me to go into it, you can let me quickly know at the comment section, and then I'll take time to do that. Now, I have done a graphical representation of this I would want us to look at so that we appreciate it as well. This function here, this graph here, we see is the graphical representation of this. We are looking for its limit. So this is what we have here. And we want the limit as x approaches 0. This is our 0 over here. And as we can see, if we trace out to this point, we are going to trace again to the corresponding y value. And as you can see, that gives us a 5, just as we solved. All right. So if you can't solve it using algebra or calculus, then we are just going to use what? Our graph. That is, if you have the means to plot. Let's go to our next question. Okay, so this is our second example. In this second example, we are looking at the limit of tan x over sine x. Now, I would want you to know that when it comes to the limit of trigonometric functions, there are easier ways of doing it using differentiation. But because we haven't done differentiation yet, we are using the method of substitution and then using other trigonometric identities. Later part of this series, we'll look at differentiation, and then we would look at how to apply differentiation in solving limits of what? Trigonometric identities. So let's go into it. We want the limit of tan x over sine x as x approaches 0. So we have the limit of tan x, the tangent of x, over the sine of x as x approaches 0. Let's take note that the tangent of x can be written as the sine of x over the cos of x. So for that reason, let's rewrite this, which is tan x over sine of x as the tangent of x multiplying the 1 over the sine of x. Then we substitute sine of x with what we have over here. So let's quickly do that. This gives us the limit as x approaches 0 of substituting the tangent of x. We have sine x over cos x, then times 1 over sine of x. So sine of x. Now looking at it, you realize that this sine of x can cancel out the sine of x. And what that would mean is that all these that we were looking for has then been simplified to what? The limit of the tangent of x over the sine of x as x approaches has been reduced to what? The limit of 1 over cos x as x approaches 0. Using direct substitution, remember from this diagram, the limit of cos of any value is just evaluating the value itself at that point. You see? So we are coming to apply that same idea here. So this here is going to be what? Using direct substitution, we have 1 over cos 0. And the cos of 0 gives us what? 1. Hence we have 1 over 1, which is equal to 1. So this simply implies that the limit of the tangent of x as over the sine of x as our x approaches 0 is equal to what? 1. So basically these are just the limits of some trigonometric functions. Alright, and as I said earlier on, you can use differentiation to do most of this simply. So at the end of this playlist, if we are done with differentiation, you would understand how to use differentiation and other methods to work these ones. This is a graphical representation of what we just did. So this here is the graph of our line tan x over sine x. And as you can see, as our x values are approaching what? 0. What are we getting? A value of 1. That is it for this one as well. Now there are some special cases and limits that you would also have to know. That is when a value of x approaches infinity. Because sine x and then cos x are oscillating. Let's see their values here. So this is sine x. You see, it oscillates in this order. And this, on the other hand, is cos x, which oscillates. It ranges between what? 1, positive 1, and then negative 1. Sine also ranges between 1 and then negative 1. Because of this condition, we say that they do not have limits when x is approaching infinity, because they will always be in between negative 1 and then 1. Hence, the limit of sine x as x approaches infinity does not exist. Now, there is also special cases where we apply the L'Hopital rule, which we'll be doing when we get to differentiation. These are some questions here you can quickly try based on what we have already done, and then see or test your understanding on what we've done so far. Thank you, and then see you in the next video where we look at the limits of functions as x approaches infinity.